Okay, hello and welcome to third day of the Observatories forums, and hello also to everybody online. Hopefully you can all see the screen sharing. Cesar, if you can give me a thumbs up.
Yeah, I can see it.
If not,
Can I start
it's
sharing my
interesting.
screen?
Okay, 1 second. Let me try that again.
Let me see. Do you see it now?
You see it now. Perfect. Thank you very much. Okay, so before we begin, just the usual range of logistical announcements. A reminder of our code of conduct. We are following the AES Code of Ethical Conduct to encourage the free exchange of ideas and to avoid any demeaning or diminishing of other people's contributions. So please be respectful in all your interactions. Any questions, come to me. So our day 3 agenda looks like this. We have a session with science with AEON. We have an unconference session, and then we have some time domain science to close us out for the afternoon session. The rest of the time I've left as unconference sessions. I know some people have travel commitments to meet, so we'll keep it flexible. And that time, as before, is your own. So please figure out what you want to do with that time and post ideas to the Slack channel if you want to coordinate with other people. And most of you, I think, have found the unconference session ideas table. You can vote there, or you can add your ideas via the canvas on the Ops Forum Slack channel. And I think that's it for logistics, so I will escape out of that. And then I will hand over to Cam Whipper, who is kindly going to chair this session.
All right, good morning, everyone. Welcome to the third day here. As Rachel said, my name is Cam Whipper. You may remember me from the very last talk of the first day. So I will be the chair this morning. So we'll just get started here. So our first talk is by Cesár Briceño. He is on Zoom, so let me stop the share here. And hopefully we'll see you in a second here, Cesár. All right, we can see you. Go ahead.
Excellent. Okay, so good morning, everybody. Pleasure to be here. Would have been better to be there in person, but well, not always we can travel. Special thanks to Rach and our Las Cumbres colleagues for organizing this amazing workshop. It's been really interesting so far, and I'm pretty sure it's going to be very productive. So today I'm going to talk about how we have implemented AEON on the SOAR and Blanco 4-meter telescopes. For those of you that do not know me, I'm Cesár Briceño. I'm the SOAR telescope director, and I've been a project scientist for AEON SOAR and Blanco since we started the project. So I'm going to tell you a little bit about how we got there. So I'm not going to dwell on this. You already know about the time domain ecosystem, and AEON is the facility side of it behind the TOMs and the brokers. And AEON, the Astronomical Event Observatory Network, as we all know it, was born as a collaboration around 2018 between NORLab and the Las Cumbres Observatory. And the aim at that time was to develop and promote a network of programmatically accessible and dynamically scheduled, very important telescopes. And we were building on the extensive experience of Las Cumbres running a distributed network of telescopes to bring in the big guns like 4-meter class and 8-meter class telescopes into that system. So from the start, one of the things that we defined was what is an compatible facility like. And one of the clear things that probably most of you already know, such a facility needs to have APIs that are capable of talking and accepting observation requests and also broadcasting the status of those observations and the facility itself. Of course, whether the facility is available or not, whether a particular instrument in the telescope is available, and once the observation requests are started, uh, tell the system that an observation has initiated and when the observation has completed, and as much detail as you want to give back telemetry reporting during the observation. There, of course, it needs to have a queue observing mode. Ideally, it would be dynamically and automatically scheduled. And of course, it needs to have a data archive of some sorts for both the raw and the reduced data that is accessible via an API access, in addition to any other forms like web forms and so on. We also like, as a desirable, if we could have real-time data reduction, and we'll go into that a little bit further. So the initial goals were, yes, to develop the interfaces, particularly the API. We needed to connect a facility such as SOAR, for example, and then Gemini and others to the network and being able to submit observations to that telescope. We started with SOAR as a Pathfinder facility because SOAR was a non-queue run telescope. So it was a perfect example for incorporating into a network a telescope which is normally not run in queue mode, such as Gemini is, for example, and see what were the challenges and how we could add it to be run and fed observations via APIs and so on. We decided from the beginning that we would run SOAR using the existing LCO, Las Cumbres automated scheduler, which runs unsupervised, and it would execute an automated queue on dedicated nights that we flag as AEON nights. I mean, those were nights that were scheduled to be run in this AEON mode queue. We also wanted to encourage data pipeline archiving efforts. Of course, add then Gemini as a larger telescope via APIs. That was easier because Gemini already was fully queued. Investigate another of the tasks from the beginning was set out to look at new tag processes that would streamline the process for users to apply for the network facilities that AEON would be offering. And of course, start getting ready to add other telescopes like Blanco, Rubin in Kind, and so on. So let me talk for those of you that don't know much about SOAR. SOAR is a 4.2-meter telescope. It's located in Cerro Pachón here in Chile. It's co-located with Gemini South and Rubin. So it's placed in an ideal position together with Gemini to work as a follow-up machine for Rubin targets. And the other interesting capability it has a suite of instruments which are always mounted and always ready. In particular, we have optical and near-infrared spectrographs and imagers among most of the workhorse, among some of the workhorse capabilities. So that means that users can easily request one or the other telescope, and we can switch from, instrument, and we can switch from one to the other in a matter of seconds or a couple minutes at most. So there were certain constraints that we had on how we wanted to define the AEON implementation on SOAR. First, we knew that SOAR was not and would not be a robotic telescope in the near or mid future. Therefore, we will always have a telescope operator on site. Now, this may evolve into the future to the telescope operator being, remotely in La Serena, maybe like Gemini has. We don't really have any plans to do that, but even if that happens, still you have a telescope operator running the facility. It's not robotic. But on the other hand, we couldn't afford to hire additional staff to operate a queue. That especially, turns to be necessary in the case when you have a queue that you want to be highly intervened by scientists and so on. Easier now with AI, but at that point we were clear that we did not have the funding to hire people to just run the queue. Therefore, that placed important requirements in that the queue should be automated enough so that it could be run by telescope operators with minimal supervision by staff scientists. This was to the point where we did not want the telescope operators to have to be making scientific decisions on the fly on whether you want to prioritize a target over the other, you want to or move one target down in the queue and so on. That kind of decision making or burden we do not want to fall on the operators. Therefore, that turned out in running with a fully automated queue that was generated externally, in this case by the Las Cumbres automated scheduler. This queue was non-editable, no decision making again required the telescope, and the telescope and instruments would need to be highly automated so that they could be actually run by an easy-to-use software tool. So I'm not going to go into the details. This is really, old stuff, but we started implementation and the first interface demonstration by the end of 2018. And basically by mid-2019, we had a mostly full operational system that we started testing with real science programs on Sky. So how does, and again, this is mostly the operational aspects of AEON on SOAR. The scheduling, the way we do it is we pull together all the requests from the different programs that every semester have required or requested for AEON mode time on SOAR, and the sum of all the approved time for those different projects divided by 10, it's a rough average, is the number of nights that we're going to schedule in AEON mode. We currently work with only two types of targets, which are those described yesterday by John. The target opportunity targets are given higher priority because they are ingested into the queue as time critical. This means that time critical targets skip the queue once they get into the queue and position themselves on first place into the queue. They are not disruptive. They do not interrupt the ongoing observation. The ongoing observation will finish. But then the next one is a time critical target. Of course, is there more than one time critical target? They will just fight for the first place and end up ordered in some particular way, depending on other constraints like position on the sky or mass limit and so on. And then we have the normal targets, which are all the other ones that just go into the queue according simply to the main constraints. Position on the sky, time window, air mass, moon phase, moon distance, and so on. The data access at SOAR is we provide data access, observation status, so people getting either through the API, but mostly through the Las Cumbres observing portal, they know whether the observation is pending, whether it has been completed or it failed. The data are accessed by using the Las Cumbres web portal and Science Archive. The data are also sent to the NORLab Science Archive in parallel, but most people really use the Las Cumbres Science Archive. We may change all the regular programs have the same priority and all the target opportunity programs have the same priority. This may change in the future. Las Cumbres has the capability built in to do different priority to different programs. We have not exercised that capability yet. So what are the science capabilities that we offer? We offer long slit spectroscopy, basically from the UV atmospheric cutoff out to 2.2 microns in the K-band. The optical part is done with the Goodman optical spectrograph. It's a very highly configurable spectrograph, but in AMO, we mostly use the 400 line grading, which gives with a 1 arcsecond slit and 2x2 binning, that gives about a resolution of about 500. That's the most popular mode. Two setups span the whole optical range from the UV cutoff out to 0.9 microns. And then the triple spectrograph is a cross-disperse instrument, is R of about 3500, fixed, is a non-configurable spectrograph. Goodman also is an imager instrument, and it provides a 7 arc-minute wide round field of view. We normally have the Sloan filter sets, but we can install others, and some AEON programs have used other filters. And we don't still we have a near infrared imager on SOAR. It's not yet incorporated into the AEON because we're expecting it to be replaced with a new infrared imager. That one will be added into the suite of AEON compatible capabilities. We were expecting to have that ready by now. It's been delayed by several reasons, so maybe it will be on the telescope starting next year, calendar year. One of the features is that the Goodman spectrograph has the ADC, the atmospheric dispersion corrector, always in. So that means that people can use any position angle that they want, which allows for larger flexibility and better image quality at higher masses. And we have real-time data reduction for the Goodman data, not so for triple spec. For Goodman, for the optical, that means that that people get both the raw and reduced data, spectra, and images for Goodman, and they get the raw data for triple spec. Those they have to reduce on their own. In terms of operational features, we have I said already, a dynamic queue. This is parsed by custom software from the Las Cumbres Robotics Scheduler software. It controls everything, so it sends the automated slews, the instrument configuration, switches from one instrument to the other. That's completely unsupervised. Our system has non-sidereal tracking. When a non-sidereal target comes in, the system automatically, it doesn't have any position, any other information other than the target name or the orbital elements, which is the default. And the system does a query to JPL horizons, queries the ephemeris, and slews the telescope and sets the appropriate tracking rates. We have automated selection spectrophotometric standard at the beginning of the night. We can override that manually, but and the observation is completely unsupervised except for putting the target on the slit. Even the exposure times are automatically set. Same case for the telluric standard. People do not need to specify a telluric for the triple spec observations. This telluric is automatically selected from a long list of A0 stars throughout the sky, and it's automatically included into the observation for every target. The only manual parts we still have are guide star and target acquisition. And we also have night logs that are automatically generated and emailed to the users at the end of the night. So just to give you a quick flash visual idea, this is how the an observation request looks on the Las Cumbres observation portal, web portal. This is how observation requests using the API for SOAR works, with the different visibility windows, lunar distances, and so on. And well, we have, as I mentioned before, we have been running AEON on SOAR since 2019 B semester. In 2025 B, we have 26 programs, 19 regular, 17 OO. We have scheduled 27 nights. That's not much, but you think that we had a schedule shutdown of 7 weeks this semester for the coding of the primary mirror. We have now, as of this week, postponed that to next semester. So we're going to put back a lot of all that time into science. And so that number of nights is going to grow. But in general, this has turned out to be a very highly demanded mode at SOAR. We are doing lots of time domain and MMA signs that you can see there, spanning from, extragalactic, of course, to solar system and so on, even non time domain things, but critical like LSST photometric calibration programs with using white dwarfs. We have already a number of science referee science papers, many technical publications. And as I mentioned, the demand has been going up. Now we're getting on average about 50 plus nights in AEON mode during each semester. As I said, this 25B is just because of the constraint of the shutdown, and this will likely go back again to about the same level as the previous semesters. 65% of the 2025 B SOAR survey proposals, they're not all in AEON mode, but most are just to complement Rubin observations once they start the survey. So this is how people think it's important for SOAR as to complement Rubin capabilities. And I'm not going to get into this because Hannah is going to give a really cool demo on the observation schedule manager, which is the SOAR, the interface and the backend that we use to talk to the La Cumbre scheduler through the APIs and so on. This is open source software. It has been published in SPIE, and this is just how it looks. This is what our operators see when they're running the queue, that you have down here the incoming queue, and on the right, lower right, the observations, the outgoing queue, the observations that have been already executed. And here in the middle is just a staging area where the operator can keep track of each of the steps of an observation and the exposure time, and they can, pause or cancel an observation here if something goes wrong, and so on. We have one of the nice features. We ask people to provide finding charts, but in case they don't do, our system is connected to Aladdin, so we can always pull the Aladdin image for DSS image for that target. As I said, we have some real-time data reduction. This is provided by the Goodman spectroscopic pipeline in its live version. And this is really cool. It means that you get about 5 seconds after shutter close, you get a 1D wavelength calibrated spectrum. True is mostly right now good for a quick look. As mentioned by Griffin, there's still issues with the wavelength calibration. We have some, in part because of resampling issues and so on, that we're working on. And so updates or fixes are coming up. But as I said, this is the kind of data people get. They get the whole raw data, but also the fully reduced and the intermediate steps. I mean, they get, for example, the extracted spectrum. So they could use the extracted spectrum and then do their own wavelength calibration if they want to, if they don't trust the one that we provide. Not only that, but this system, this data reduction is fully integrated with the night logs. And so any comments that you write here that the operator or the science support person writes here on a particular object will show up in the night log. And so the people will have that, the users will have that information when they get the night logs. So the observation schedule manager, the OSM, the Goodman spectroscopy pipeline, and down here, the nightly observation logs are all web-based systems that are fully integrated. This is how the night log looks. So you can, we have the scale, you see the schedule of AEON nights, and the ones in lighter green and the ones that already have happened, and they have a night report associated. And you look at the night report, this is what we see. And then the telescope operator or the scientist can write any comments, about a particular observation, about technical problems that we had during the night and that may affect the data and so on. And that will go to the users. These are the logs automatically generated from the image headers. There's no intervention from any person here, of course. And this is what the users get via email. They get a sort of a summary. And this is all one long thing, but I just put it here on two panels, and they get all the details about the observations, and so on. So this is the workflow of how we run AEON and SOAR. You have the person up here that is going to be in their computer using via either a Tom plus an API or the web portal. They will submit observation requests to the Las Cumbres scheduler through the API that talks to our observation schedule manager that runs that will send commands to both instruments and to the telescope control system to slew things and so on. And then it will also administer the sending of the data to the Goodman pipeline, or if it's triple spec, directly to the archive. And then the Goodman pipeline is the one that takes care of sending back the raw and reduced data to the archive. So what are the next steps? And I'm going to go quickly, but we want to incorporate the near-infrared imager. That's a 5 arc-minute field of view. This will really complete all capabilities of providing full optical near-infrared imaging and spectroscopy on Blanco on SOAR. And we want to automate guide star acquisition and on-slit acquisition. And there are some features like allowing the SOAR operator to delete targets from the queue that's sometimes necessary, we've found. Is something that we're working with our Las Cumbres colleagues to do. And now we still have to convince our Brazilian colleagues to join and start using AEON. That would provide a larger pool of nights that will improve all the cadence and the possibility for people to do better science. So finally, how are we with Blanco? We're implementing AEON on Blanco also. Blanco is a powerful time domain machine with DECAM and new firm. Its wide field capabilities, that's strong. New firm is an imager, near infrared imager that provides a about 27 by 27 arc-minute field of view. Again, the requirements were similar to SOAR, and so we follow essentially the same path to implement AEON. And we started with new firm because there was specific NSF funding to do that part of the software. That's why we started with new firm and not DECAM. So now the AEON capabilities on Blanco are wide field, will be wide field optical imaging that will be super powerful to complement Rubin. And of course, wide field near infrared imaging that will provide a different wavelength range that will never be covered by Rubin. The new frame implementation, I'm not going to go into the details, but basically we were able to run a night of fully automated observations back in February, where we had a schedule that was generated through the portal at Las Cumbres and then transmit it to the scheduler and download it into our software directly from Las Cumbres and execute it at Telescope. And that went very successfully. And now we are switching at the point where we're switching Blanco to actually run in AEON mode on specific nights with new firmware, starting next week, I think, is the first run, and we will be starting running at least half nights with it in AEON mode. The next steps are to streamline our AEON new firm operation during this semester, and then we hope to start the AEON implementation of DECAM at the end of this calendar year or beginning of next one. And this is very similar. Again, this is just the AEON workflow on Blanco. It works the same. The only difference in Blanco is that DECAM or new firm are exclusive. Either one or the other is mounted. They're both operated in campaign mode. So you can never do switch from one to the other in the same night. So we have several nights with new firm, and then about 2/3 of the time DECAM, about 1/3 of the time will be new firm on Blanco. Thank you.
All right, thank you for that talk. Maybe one quick question before we move on.
Since time domain can get so much more out of many more SOAR nights, why aren't all SOAR nights or more SOAR nights available? Why aren't all nights on SOAR? Sorry, not SOAR nights. AEON nights. Why aren't all nights on SOAR AEON nights?
Sorry, can you say that your question is why are not all nights on SOAR AEON nights?
That's right.
Yeah. Okay. Yeah. Well, we have different partners and they have different interests, and not everybody wants to do time domain. That's one thing. Then SOAR is seen and used by several of its partners as an important training platform for its for grad students, for young scientists, and so on. And that's better done in classical mode. And then finally, there are some scientific programs that simply are not a good match for AEON. For example, if you wanted to do a planetary transit, you're going to be sitting on that star for the next 5 hours, 6 hours. Okay, there's no way a 5 hour, 6 hour long blog is going to fit into an AEON queue, not easily, certainly. And so that's in that case, what we prefer is, here's your half night, do your planetary transit, and then the other half of the night we switch to AEON mode, for example, or something like that.
But that's
And
not
so,
true. LCO does planetary transits all the time, and they will absolutely fit in the schedule. And so do classical observing. That would also fit. It doesn't matter if it's time domain; it would still work just the same.
yeah, but there are people that really want to do their own observation, and we cannot override. We have to cater to the interests of the different stakeholders at SOAR, which are the UNC, MSU, Brazil, and then NORLAB. And NORLAB is which is within which we started developing AEON is 30%. Now we have Michigan State University and UNC has started putting some of their time, not all of the time, but some of the time into the AEON pool because they recognize how useful and powerful it is. And so we now have more time. And again, we still have to get our Brazilian colleagues to get on board on their hand, and then we'll have even more. I don't think we'll ever go to 100% Q, AEON Q.
Okay, thank you.
Yeah,
All right. Thank you. Let's thank our speaker again.
thank you. I'll stop sharing.
All right. Our next speaker here is Hannah, and she's going to join the Zoom, and then we'll hear a little more about SOAR and AEON.
Bear with me here just one moment. How's that? A little bit better. All right. So, sorry, I'm going to share from my laptop today since I'll be doing a demo. But hello, everyone. My name is Hannah Crayton, and I am a full stack software engineer at Noir Lab. And I work with Cesár Briceño on the technical implementation of operating SOAR and Blanco in queue mode to be part of the AEON network. So today I'm going to be talking a little bit about what the actual software behind AEON at SOAR and Blanco looks like. And let's just dive in. So I'm going to just, it's changing on my screen, but not this screen. Okay, give me one moment. We even tested this morning, guys, I promise. There we go. Okay, we'll do it like this. All right, so I'm just going to be talking about the observation schedule manager, which Cesár briefly introduced, and then just jumping into the architecture and code breakdown of how we actually make that happen. And then I'm going to follow it by a simulated demo. We've actually never live demoed this ever, so I hopefully don't eat my words, and we'll see how it goes. So yeah, the OSM is basically the interface that connects our queue to our instruments and does the actual science. This was developed back by one of our senior engineers, Diego Gomez. When I joined Noir Lab, I came into the project and now maintain and develop on top of the code base he created. But I wanted to just shout him out because he really built this from scratch, and it's what we use today. So just a workflow concept review before we jump in, kind of reviewing what Cesár already shared. So the concept is astronomers can request observations to be queued at AEON facilities with LCO scheduling algorithm. On the AEON specific nights, our telescopes query this dynamic schedule to execute a queue of observations programmatically. So Noir Lab's solution to automating the execution of the AEON queue on SOAR and Blanco, given that they're classically observed telescopes and didn't have that format before, our solution to that was the OSM, the Observation Schedule Manager. So the OSM, in simple, is a web-based application deployed at SOAR and Blanco that automates the entire observation life cycle. So what does that mean? That means the OSM is receiving the schedule from LCO and conducting and managing the queue, making sure that the things are executing that need to, the ones that are up next. If we have rapid response or TOO, that they're taking priority in the queue and are the next ones ingested. So once the observation block is what we call a request coming in to be executed, once that observation block is ingested, then it's actually also executing the request with the telescope control system and the instruments to actually produce the science. Once it's completed doing an observation request, it's also doing data management to make sure the images are going where they need to, as well as any telemetry reporting and feedback we give back to LCO for them to better enhance what's coming next in the schedule. I forgot I did all these fancy highlighting things. All right. So jumping into the architecture and kind of code breakdown of what that looks like. So we have some Docker fans in the audience, I know. Conrad, this is for you. So the OSM is comprised of containerized microservices that take care of the different areas of the OSM's ecosystem. And what does that look like visually? I bet I did my best here. So each of these dark blue rectangles represents a Docker container. And the OSM is comprised of 5 main containers. So just kind of briefly going through to give you an idea, what I'm referring to for this presentation, our first and primary container is what I'm calling our core container. And that's where really, for me, all the magic happens. That's what's actually communicating with our TCS and our instrument specific class files, managing the workflow, execution. This is dealing with controls. It's sending the actual low-level commands to the instruments and doing all the logic for us. The uploader container facilitates the image uploading to LCO for SOAR because we do give data back right away to be accessible in the portal. For new firm on Blanco, we're not doing that data transfer. That's going to go, that just goes straight to, they're very large images. So that goes just to our NORLab archive. But then John worked with our archive team and John Nation at LCO worked with our archive team, and they have a cool feature to make it easier for LCO users on the portal to access their data right away on the NORLab archive instead of kind of looking blindly. We have a database container that is the database of the application, has a lot of information there, telescope specific instrument configurations, I mean, really and a lot of other data as well. Our web container is our web-based application interface for the user, which you'll be seeing shortly. And then a simulator container, which for me was kind of one of my big goals after coming, was making sure we built up a simulator suite that simulates the entire operation with the telescopes and instruments for integration and testing. Because if we're adding a new feature to the OSM, or there's a new command or logic workflow that the OSM needs to interact with on the telescope level, I don't want to test that for the first time on SOAR with the 4.2 meter mirror and a very expensive robot, if you will, and break something. So instead, I hook up the OSM to a simulated version of the telescope that will send me the real feedback and commands and responses I would get from the instruments or the TCS simulating the operation of the telescope, and find out where my code breaks with the simulator before I plug into the big robot. So OSM as a multi-telescope model, this is new for us because it was used just exclusively on SOAR. We are now in production with Blanco, and actually I'm going to correct Cesár from the previous talk. We are already in production with Blanco. We already had our first production AEON nights a few weeks ago. I got to stay up at the telescope a few nights and make sure that was running properly. And it went really well. So we produced data. We got it back to the users. And actually next week we have a 4-night new firm run. So it's very exciting that Blanco joined the ecosystem for us. And now our nice grandfather Blanco is also operating in a fancy queue format on AEON nights. We didn't know if we'd see the day. So it's pretty exciting. But yeah, it's... the application is locally deployed on site at the telescopes. It's really important for the engineers to have the server right there. Given that it's doing real-time communication with our instruments, we didn't want that coming from Los Serrano base facilities. We have all sorts of network issues sometimes. We didn't want latency, and so it's really important that the server that's actually running everything is co-located on site. So what that means is we have a common deployment. So those 5 principal Docker containers that I mentioned, those are all deployed. It's a common deployment. So the same 5 as they are deployed on SOAR and Blanco, it's telescope agnostic. But then in that specific server for either telescope, we do have a server specific environment file that's going to give you information for that specific telescope, like maybe data paths, making sure that on that telescope, what versions of those containers are we running for maybe certain reason. Blanco has a different version than SOAR, and a variety of other variables. So that's deployed on each telescope. Going back to what that core architecture is, I'm gonna specifically get into how the core is built, and then just to orient us a bit more, I'll go through it since Cesár kind of reviewed it as well. But to give you an idea of how everything connects together. So our core container is what's interfacing with the telescope control system and the instruments, and is the conductor. It's making everything happen. So that's interacting with our web app, right? So and vice versa, the web app is populating what's happening with the core container. As the core is executing the different steps and workflow with the instruments, it's giving visual feedback to the user at where we are in that process to our web application, both obviously working with the database and sharing all sorts of information. Again, there's the core working with our TCS in our instrument, and then giving feedback in real time to the database. Where are we at with observations? Here's a list of images being done. The database also getting information in real time from the core and populating the web app. And then the database has the list of images that were performed with by the OSM. And then they work together with the uploader to say, hey, LCO, we have 20 new images. These are destined for LCO. Please send that to their API. So again, core is receiving the schedule. from the observation portal, interacting on that side, and then web with our users, our telescope operators. All right, so going back to the core and breaking it open now, the core elements, it's a bit more complex than this, but for the sake of the presentation, just from a very high level, the main components, we have an instrument class, we have a TCS class. I'm going to talk about the observation request JSON, how critical that is, and then an instrument simulator. And so I'm going to use NewFirm as an example. NewFirm's been my whole world for the last 2 years getting this integrated. So I thought I'd give it some time to shine. So breaking down the OSM or the core, if I use NewFirm as an example, within the core, what we have is a NewFirm class that was created. Before, we only had a SOAR TCS class, Goodman class, and triple spec class. Those are the instruments that we use at SOAR. But now bringing in Blanco, we needed to create not only a NewFirm class to be able to handle NewFirm operations, but also a Blanco TCS class. Our TCS between Blanco and SOAR are very similar, so a lot of the work was already done, but it still needed to have its own, has nuance. So what does that mean? The NewFirm class is what facilitates the communication between the OSM and the NewFirm instrument. And then it also organizes and executes the logic needed to carry out NewFirm steps and workflow to observe. So the NewFirm class is what's deciding, based on the information I have from this observation request, this is the exact command I need to send to the NewFirm instrument, and then sends the command, is polling, understanding the response from the instrument, making sure that we have the validation and verification we need to go to the next step, knows what that next step is that NewFirm needs, and is facilitating the actual command workflow to have the instrument perform the steps it needs to get the science. And then exact same thing for TCS, right? So the Blanco TCS class is what is within the core code, is what handshakes with the TCS and says, all right, it's you and me. This is the target I'm going to. Okay, great, we're at that target. I need you to slew. Okay, we're slewing, etc. Then the observation request JSON. So this is very critical for us, and this is where we collaborate a lot with LCO. Basically, John and I negotiate. I say, hey, NewFirm needs XYZ information in order to execute an observation. These are the parameters required by the instrument to operate. And then he tells me, all right, well, here's how we can deliver that information. Here's what will require the user to input. So just quickly breaking down what that looks like. It's a long JSON that we define the structure of. You're not going to be able to read any of this, so we'll go quickly. The request within it, different configurations, depending on what the user wants. We're defining things like for NewFirm, this is actually triple spec JSON, but within instrument configs, what does triple spec need in order to execute? So exposure count, time, any extra params. For NewFirm, we have dithering, so what's the dither pattern? What's the dither value? Target information. So the core code receives just this JSON, and based on that JSON, knows what instrument it needs to communicate, what are the commands to execute the entire workflow. And then again, if we integrate any new instrument, or in this case, a whole new telescope, for me as a developer, my priority is creating a simulator that will reflect exactly the behavior I expect from the instrument we're in production for testing. All right, so we're gonna attempt a simulated demo now and see how that goes. So I thought, okay, so we're in still. So this is my attempt at showing you what's on the actual mountain right now. I apologize, I know this is not a great visual for people in person. It's a long story why we have to access things this way. But this is the OSM interface on SOAR right now on the mountain. So this is, it's currently powered off. We actually have an AEON night tonight, so operators will connect and get this running. Everything is red up there, which tells us that we're not connected to an instrument or a TCS, which is good. I'd be in trouble if I was right now doing a live demo. And right here in previous observations, we had an AEON night 2 nights ago. And if we open this up, we see all the information from the requests that came in that we executed. So I'm gonna, and then I guess I just want to shout out what Cesár was talking about up here too. On our SOAR server, we have the GSP. So this was, it's so slow. This is the Goodman pipeline. So for instance, that was the the data reduction that he was talking about, that the users have access for Goodman, is what that looks like right there on the server. And then just an example of what the logging system, he said, where our operators are seeing what images are coming out, being executed by the OSM, and then any notes. And now we're gonna close that. And what I thought I would do is just walk you through what that actually looks like on a screen from an operator perspective when we receive a request. So this is the OSM. Let me see where I'm at on time. Great. And as you see, my local server, so I'm just running this, it's deployed locally on my laptop with the simulator right now. So I'm green, but I'm not actually connected to a real telescope. I'm connected to SOAR right now. My simulator's on SOAR. I'm connected to the simulated TCS instrument, and my core code's running green. And so I thought I would just mimic what it looks like when we have an observation come in. Typically at night, our operator is going to make sure once we power everything up, we have 3 green lights in the left. Then we're going to make sure that we connect to LCO. So this connects us to the network, lets LCO know we're online, we're ready for observations to execute. Please send us a queue. And then once we hit play on resume queue, that puts everything in motion, and then things will automatically enter and execute, and the operator can watch the workflow. Since this is deployed locally, I couldn't actually bring in an observation from LCO, so I thought I would submit my own. We have our own version of an observation upload because we use the OSM on AEON nights to operate in queue format, but we have the technology to operate in a queue always, technically. We just rely on LCO to tell us what to execute and when. So what we decided to do is create our own version of being able to create that queue. So then astronomers who are comfortable with the OSM, if they have classical time, but they really like observing in a queue format instead, and they don't have to do any of the work with the GUI and manually enter everything, they can enter their own schedule into the OSM, press play, and operate in a queue format on a classical night. So this is actually a new feature. It's just grayscale right now. This isn't the final application. Cesár hasn't even seen this yet. So Cesár, this is finished. Yesterday, I got some help with giving an example request. Griffin is one of our very frequent SOAR users, so I used his science, his science example. So observation name, request type, we have different types, of course, submitter, observation window. I'm not going to go into all the details here, but target information, instrument information, and instrument setup. This is going to look different based on telescope and instrument. But if I go ahead and submit this, all right, that's a good sign. That should populate here. There it is. Okay, so we'll pretend that we connected to LCO and they sent me the queue that we're going to observe, right? So I'm very nervous, but I'm going to hit play. I'm pretty sure I'm connected to the simulator and not the real telescope. Cesár, let me know if the dome's moving. But so I went ahead and hit play. We're in queue mode. And this is going to happen quite quickly. And you know what? I was going to show you logs, but I think that's maybe just cool to me and not anyone else. But okay, I won't do that. So I'm going to hit play. And a lot of things are going to happen at once. I think I had exposure time 20 seconds. So it gives me something to explore. Okay, so we hit play. It entered into the execution plane. We're setting up the ADC to 50 in the Parker probe. Okay, so what we have here are the different steps of execution. So we have all obviously the request information up here. And right now we're on the camera step, we're on the gear and target step. They're pending, they're yellow. If I look at my logs right now, what it's telling me is I'm polling the TCS and we're slewing. I'm also moving gears, which is if we have any filters we're moving to. So mirror and lamps are completed. These are sectioned out in what we're able to do in parallel. So mirror and lamps, we can do at the same time. Those are done. Right now, we're working on target. That's probably our longest step. And we're working on the gear step. Camera is already green. Those 3 things happen in parallel because we're able to slew to target, do gears step, and send all of our camera parameters to the instrument for header information and whatnot at the same time. So what we did here is right now, because I wasn't on the screen, there we go. that all finished. We finished the rotation step, and now we're on the alignment step. So this is kind of the opportunity where now for the first time, the operator is getting involved, and all the operator does is, okay, do I need to align something or do an acquisition? And I want to point out too, this is the feature that Cesár was saying with Aladdin. So if the operator wants to see what are we looking at, what are we pointing at, they are able to see that target there. When the operator's done an acquisition or whatever they want to do here, acquisition done. And now we're going to move into the exposition step. So right now, it's letting you know what your exposure time, readout time, exposure count. And on my side in the logs, which my window isn't going to, I'm seeing real time the commands and feedback from the instrument. What is the OSM telling the instrument to do? And what is it letting us know it's doing? So I did a really simple example. I just had one configuration, spectrum, up in the upper left. It's yellow because it's pending. We're currently in that execution. Down here, these are the different specific instrument configs that I would have. In this case, I just have one, yellow, pending. But a request may come in, thank you. A request may come in and we'll have several tabs up here, right? Depending on how complex the request is. Or down here, it'll break down what are all the different instrument configs that the request has. But I just chose one of each to give an example. So we're still observing here. We're still exposing. We have one of two finished, and now we're done. So it came out green, which is great news for me. It's bad if it comes out red. It means there is an error. But if we open up that observation, and then again, when it came in the queue, we could open this up and see it as well. If we open it up, we have all the information of the request, what the configuration was, what did we observe. If it's green, it was successful, it was completed. If it's red, I'll get a big fancy error message, and the operators can open that up and see why we had a failure. And then just real quick before I wrap, I thought I'd show some of the other features. So this OSM actually, this might be the last time you see it. We're redeveloping this whole application. The front end is going to be brand new. So this was built, really optimized for SOAR. We have all the information we need for SOAR, but this is what also runs on Blanco. But from a front end perspective, I personally would like it to be very dynamic based on the telescope it's deployed at. With that environment file, the OSM would recognize which telescope am I on, and then on this panel will show different information that's telescope or instrument specific. And there's a lot of really cool new features we want to do. So we decided we're going to rebuild the application. And some of what this application does have, though, is I thought I would show the operator when they get there. You're able to do focusing. You're able to run calibrations, go through, choose your instrument. We have all the calibrations, define, execute, flats, focus, bias. And then from connecting it back to LCO from the image side, the operator is also able to go to the image tag and see exactly what images are reproducing in real time, whereas the destination, these are all test images, but normally it'd be a green check mark letting you know that this was sent and confirmed to arrive to LCO, and the user has the data, and that happens in real time as we're executing. So I think this was a lot of information at once, but an idea of what the OSM does for us here to operate in queue mode. So if anyone has any questions, I'm happy to answer them. Uh-oh. And I just want to point out, Javi just arrived today. He's one of our software engineers at Gemini North. He's in town because for personal reasons and came by to support. So if anyone has any Gemini North questions, we have another NORLab engineer.
Thanks, Hannah. Conrad from CFHT. Brilliant setup. My question is like when if you go to the slides with all the Docker containers and like you have the observational control system like going to the simulator, what's the protocol to communicate with that? And then also like what was some of the challenges you had to get the simulator going? Like, does it actually have to communicate with a PMAC, or like, is it 32-bit? Is it like, did you have problems with the older code? Like to do that as the simulator as a Docker container must have been challenging, I imagine, but how did that go?
Not necessarily. Is this the image you wanted? Or were you looking
Or
at
the like all the containers that you had in the yeah, that's the
this?
one. Thank you.
Okay, so break down, give me, what is your,
So what
what's
was
your
how
number
does
one
the
question in
web
there?
go to the like how does it communicate with this simulator? What's the protocol? Is it like
Yeah,
the
so it's
API?
exposed ports between the containers, and they know that they exist, and we have a variety of WebSocket and exposed port communication.
Nice.
But it's fairly simple. So on my local machine, in our database configuration, we identify what the IP and port is of the instrument or the TCS that that deployment is communicating with. In my local machine, that IP and port is just the IP is the simulator container with the port that I've designated as where we communicate. And so instead of connecting to the real TCS IP and port, it connects to the simulated IP and port, if that makes sense.
Yeah, and then the
Okay.
simulator doesn't have to communicate with anything else. It's just sort of running
Yeah,
the code.
it's standalone. Yeah. So you asked something about a challenge with with building the simulator. I would say documentation and then real instrument behavior changing and me not knowing about it. So I obviously build the simulator to respond the way that I'm told the instrument will respond, right? So if I send FLT get filter, I'm expecting done JX, for instance. But if Marco, our instrument engineer, changes that and then I'm not aware of it, then that's not reflecting reality anymore. We work together really well, so that rarely happens, but it's the biggest weak spot, I guess I'd say, because sometimes instrument engineers, for a variety of reasons, need to change things, and then we don't have if that communication's lost, then potentially I'm simulating that doesn't reflect reality, and then you can see where that might pose a problem.
So the simulator is a different code base than TCS.
Yeah, the simulator is just a Docker container that has basically a Blanco TCS.py file, and it is waiting and listening to receive a variety of different commands I've defined. Based on the command it receives, it has a hard-coded response that it sends or logic it follows of a sequence of responses that the OSM would expect to receive from the real TCS. It's just simulating what the response is so the OSM can operate.
Cool, thank you.
Yeah. If you have like more technical questions sometime, I can tell you.
It was really nice that you had a green light after your demo. What do you do for error handling and error propagation?
In what sense? From the human level or like code catching level?
Humans are infallible, but the machines fail. But yeah, let's say, oh, what's the other way around, I think, right? Right. No, but let's say
Here, I'll put it.
your instrument controller fails and it doesn't respond, something times out. How do you propagate that information
Yeah.
to the operator to
Yeah.
react?
So basically, if there's some sort of failure like that, is that Cesár? No. If there's some sort of failure like that, it's a very conservative, right? So we're automating a very huge, expensive telescope. We're not going to take any risks. So we have different types of errors defined, right? That if those are triggered, it's going to be very conservative and it's going to abort the observation and it's going to stop executing. It'll get outputted with a red dot. And then when you open this up, I'm sure I have failures in here somewhere. Look at this. If we open up a failure, this is all me doing different testing. The operator will be able to see, this is an ambiguous one because I was doing something very specific. Normally it's more descriptive, but there'll be a failure reason that's human readable. In my testing case, it wasn't. And it'll break down what the failure was. The operators at this point know what failures we might expect and are very familiar, and they know what they mean and maybe what they'd have to do to resolve them. But if I don't know if this is specifically what you were asking, but if it catches anything weird at all, we abort the observation. It's a failed observation. We propagate the failure reason to the operator. They open up the block, they can see why, and then take whatever remedy steps they need to.
All right, I think I have one more question on Zoom, and then we'll finish up.
I guess that's me. What are you going to write the new front end in? Which library?
That's a very fun question. So I'm building it currently in Next.js with TypeScript and React. It's a MongoDB database. I'm using Tailwind CSS for those who are interested. Is that what you're asking about the stack?
Absolutely, and that was a fun answer. Thank you.
Yeah, no worries. It's been fun for me. It's my first time building in a Next.js application. And at Noir Lab, we're trying to do things in TypeScript now and move over from JavaScript where we can. So that's been a fun battle. This current application is not in TypeScript. So
Thank you.
yep.
All right, let's thank Hannah one more time. All right, our next talk here is Brian Miller. Brian, are you ready?
Just about. I'll share my screen. Everybody hear me? Am I
Yes,
okay?
we can hear you fine.
Good.
All right, and we can see your slides, so go ahead.
Excellent. Okay, thank you very much. Very happy today to be able to tell you about some big new software projects that Gemini is working on related to AEON. So a little bit of background on Gemini for those that might not be that familiar with it. It's a NSF program that runs twin 8-meter telescopes from Hawaii and Chile, so we get full sky coverage. There's also 6 hours of longitudinal difference for time domain. We are funded by 5 full international partners. We have 2 hosts, which is Hawaii and Chile, and we exchange time mainly with the Japanese community, the Subaru community right now. We run complementary optical and near IR instrumentation at the 2 sites, both facility and visitor instruments. The facility instruments, of course, are advantageous because they have common interfaces to the whole observatory system. They're available most of the time, and 3 can be mounted at any one time, and there's fast switching, less than a minute just by flipping a fold mirror. And we operate in mostly, meaning more than 95% in multi-instrument queue, so we're AEON all the time, basically, and staff observers match the conditions constraints to the actual conditions to try to optimize for the really good weather. Here's a really quick overview of the instrumentation suite with the little boxes around things that are mostly used for time domain. We have the 2 GMOSs, which are nearly identical optical imager spectrographs. There's Flamingos 2 and Geners, which do near-infrared imaging and spectroscopy. And a little asterisk here, Scorpio is a wide wavelength from G to K imager and spectrograph that's under construction, is designed to be a Rubin follow-up machine. That's the last I'll mention about any hardware. The rest is all software. We've been running for over 20 years using basically the same software stack. We have the PIT, which we use for proposal preparation, the observing tool for operation preparation and execution and time accounting. These are desktop apps written in Java. You have to download every semester. They work okay, but there are a lot of usability issues and a lot of things we need to change in the infrastructure that really can't be done with the current software. Also, the needs of time domain and multi-messenger follow-up require some software updates. Because we do mostly queue, we do a lot of target of opportunity observing now. About 20% of the time in band 1 is TOOs. But the process is a bit manual, it can be more efficient. We do work within AEON now via Tom Toolkit plugin, but the API we have is very limited. And in this new era of all sky surveys and multi-messenger follow-up, we need to be prepared to do a lot more, and we can just make it more efficient. So we really want to get to be full AEON compliant with more capable APIs, a dynamic scheduler. And this would all fulfill the recommendations we've received from various reports on the OIR system and the 2020 decadal survey. So in 2015, we decided to rebuild the whole observing system from the ground up. This project is called the Gemini Program Platform, or GPP, with the goals to make the whole system easier to use. We replace and unify this PIT and OT. It's designed as web apps with APIs connected to a single database in the cloud. This will allow both north and south observations in the same program. It provides a lot of automation based on this 20 years of queue experience. It provides new constraints needed by the scheduler and makes more modern code that's more maintainable. This is a screenshot of our main Explore app, which is the phase 1 and phase 2 tool. And it's actually live right now. You can go to that link and try it out if you want to. So, but the Explorer is just one little piece of the whole system. So here's a system diagram of what we're trying to do. Here's Explore up here, which is talking to the real core system, which is the observing database. And the other main components are the integration time calculator. We've got the scheduler part, Observe, which is what is used at night by the observer to actually configure the instruments and take the data. So it's talking with the hardware. And over here, we have another system called Navigate, which is used by the telescope operator to configure the telescope system, do the slewing, setup guiding, all that sort of thing. So it is a gargantuan project with a lot of moving pieces. A couple of technical specifications. I won't be able to go into a lot of detail. I'm not a developer, but people may be interested just to know the generalities. It uses PostgreSQL database in the cloud. It's running in Heroku. The backends use functional Scala for the language, and we have GraphQL APIs to the front ends, which are built using React and TypeScript. For authentication, we use ORCID with the GUIs, and then you can get a user key for connecting with the APIs. A few applications, mainly the scheduler, are being written in Python. So I'm going to do a quick video demo of sort of how Explore works and how you would submit a proposal. So started with an empty proposal, and I'm going to add an observation. This actually is a sort of a TOO target, so it doesn't have a coordinate. You can, if you want to, specify a region of the sky, but by default, it's all sky. You have to specify some sort of SED for the integration time calculator and a representative brightness. So there we go there. Then you have to put in your constraints. So this is a TOO, so it needs to be fairly relaxed, so it can be done at almost any time. And this is the new bit where instead of just going right to an instrument, you put in your science requirements like the wavelength, the resolving power you need, coverage, and the signal to noise. And then on the right, you see a list of all the instruments and modes that meet your requirements, and the ITC is run, so you get the exposure times needed. And you can pick the one that you like, or you want to look at a little more. And you get the integration time, calculator plot. If that looks good, you can accept it. And then under the hood, it's calculated the whole observing sequence automatically and given the time that you would need. And then to the proposal tab, you can do the usual thing, pick your proposal, call for proposals you're applying for, put in all your COIs, do your abstract, attach your science justification, and submit. And you can always retract it up until the deadline. And also, a new feature that people have asked for 20 years is you actually will get an email confirming that your proposal has been submitted, or that the proposal state has gone to submitted. Okay, so everything can be done with that UI, can be done programmatically. Get all your program information, update, create targets, create observations and create those with the target you just created. So you can do all of that, in the Python script, and it's not necessary to, create TOO templates like you have to do in the OT now. And in order to do that, we're developing a Python client for the programmatic communication with GPP. From my point of view as a scientist who likes to dabble in some programming, the GraphQL query syntax is really non-intuitive. So we want to try to hide some of that detail and provide a little simpler interface. So we have a Python client that's under development here, and that will be incorporated, I think, hopefully into AEON Live, and be used in the GPP Tom Toolkit plugin, which we're starting to build up. And it's also being used by the scheduler, since that being written in Python and Goats, as I'll mention in a little bit. This client will also give access to improved status APIs. You shouldn't have to go check our web pages to see if we're open tonight or whatever. So there'll be a direct API for getting open, closed, and TO status, instrument configs, the weather, and so on. And this GPP client actually gives a preview of this. You can do a query up here and get the current status. It's actually doing web scraping at the moment. In the future, that'll be a direct API. But it is still really useful. I use it during the day. It's a lot easier than trying to find what this web page that you have to go to. And it might be useful for the TOMS and Heroic and other projects that want to know the telescope status. We are also working on a Gemini-focused TOM. It's called the Gemini Observation Analysis of Target System, or GOATS, which is built on the TOM toolkit. It gives us a complete and convenient time-domain workflow, especially if kind of more Gemini-related, but it can also trigger on other facilities since it's built on the TOM toolkit. It allows you to do broker queries with Antares as well as others. It'll get the Gemini telescope status. You will be able to do triggering with GPP and manage those observations. Then you can download the data from the archive and process it with Dragons. And they recently had their second or beta release, and so you can go to this URL to get that more information and actually install it and try it out. So I'm going to give a little bit of demonstration on what it can do. So you don't have, even if you haven't triggered an observation with GOATS, you can enter an existing observation, say from the legacy OCS, add that here, and then you can go to the archive query form here, submit that, and actually get the data downloaded asynchronously. You see that there's the download starting there. And then once that data is downloaded, then you can reduce it with Dragons. So here's the next one. You have the existing observation. This data has been processed already, but you can look at either process it again or look at the details of the previous reduction, including all the sort of reduction recipes that were used and modified those as needed. And you have all the documentation on Dragons there as well. You can also, once you have the reduced data, you can share it with other people via Sphere connections. I'm going to move on and show, again, right now we're building the capability for GOATS to do triggers with GPP, but this shows with a more generic TOM toolkit how that might work. So I've entered a ZTF target into my TOM. I can see that it's visible at Gemini South. So I'm going to select my program, set the conditions. Again, this looks a lot like, it acts like what the Explorer was doing before. You put in your science requirements that you need, the resolving power, and so on, just like was with the Explorer interface. It will query and give you the list of available configurations that match that. You can select your favorite preferred one and submit it. And there's the observation in the TOM database. And then over here in Explorer, that new observation has appeared with all the target information and the constraints and the instrument configuration that I had selected. And ITC plot sequence, it's been set to ready automatically by the TOM actually, and it's ready for scheduling. All right. So speaking of scheduling, we are implementing a real-time dynamic scheduler with initial funding from the NSF-funded GEMMA project. The goal is to update the plans in real time as those changes occur. The plan will be generated in less than a minute. Should improve our observing efficiency, less decisions that the observer has to make and give them a better guide. It'll schedule the two sites together, kind of a meeting network. It'll save a lot of effort by Q coordinators who have to build the plans by hand at the moment and provide these more capable APIs, as I mentioned. There are three main modes. A validation mode, which we're using at the moment to reproduce past semesters using some legacy data. So we can compare the schedule output with what actually happened and what the Q coordinators were doing at the time, and also test different scoring and algorithms. We'll have a simulation mode, which will be used the data from GPP, but sort of project into the future that Q coordinators may use for some planning purposes. And it'll be used to test also the real-time mode, which is what we'll be using at night in real time at the telescope. So briefly, the schedule architecture, the people from Las Cumbres may find this recognizable. It's sort of inspired by their schedule design. There's a collector which takes in the available observations from the ODB, a selector which pulls out the ones that from that set that are match the current constraints and the instruments that are on the telescope. Then there's the optimizer that makes the plan, and then output to observe for the observer to see and execute. A little bit, I thought we'd go into the optimizer, which is a homegrown algorithm we call Greedy Max, an attempt to codify the QC practices after being sort of dissatisfied with sort of a greedy approach, or just pick the next one in time order. And so what it does instead is it does a look ahead. So there's a period of time that it needs to schedule that has available, like at the start, it's the whole night. It goes through all the observations, finds the one with the highest score, puts it in the optimal position, meaning trying to get it close to the meridian as possible and meet all the other constraints. And then it's got the remaining time of the night, just repeat, find the next observation, put it where it's optimal, and keep going until you filled up the entire night. For this example, it actually scheduled from the back of the night, from the end of the night forward. Doing this allows you to be sure you catch like high priority targets that we have timing windows that are late in the night, and you can fill in around them so they don't get missed. And then here at the end of the night, you have the full score and air mass as a function of time. You can see it looks like probably a reasonable plan. It can also schedule multiple sites at the same time. So at each iteration, it not only looks through each open interval at each site, it can schedule, pick the best one, and then loop over. So here's an example of an early version that we had that scheduled north and south together during the same scheduler pass. If scheduled observations can be in OR groups, which they can be in GPP, so you could have like GMOS north or GMOS south for a TOO. As soon as one of them gets scheduled, the other one gets put away. And this could be expandable to other facilities. So we've actually started using GPP for early science. We call this the XT phase. Whoops, sorry. First phase was called XT0, which was the first nighttime observing with GMOS long slit, which we had back sort of in between March and June. We got some early data, and we were able to actually reduce all of that with dragons. And we also converted some 25A long slit observations and executed them at night just to prove that the whole system was working. Then as an end-to-end test, we called the XT1 process, which we had a mini call for proposals for GMOS long slit, offering about 20 hours per telescope. So we could do evaluation of again, each step in the process. That deadline was August 22. So then we had a peer review process using like our fast turnaround system. And then we started observations this week. I've been observing the last 3 nights, which is the main reason that I can't be in Santa Barbara right now, but it's been successful. We've been getting good data. Everything is working pretty well. It's been super useful at, finding tweaks and remaining bugs and things like that. Here's just an example of a plan for one of the nights, with the initial version of the scheduler. And then once that's done, we will continue with what we call the XT2 and other sort of XT testing phases as new instruments and modes are implemented, including TOOs and other features. We'll probably do it by, converting existing observations into GPP and then executing them. And we expect to put this all into operations in 2026, meaning for the 27A call for proposals about a year from now, which is actually going to come up very fast. So we've still got a lot to do. So in summary, we're providing full 8-meter class capabilities for AEON. We're constructing this whole new observing system that will support follow-up a lot better, but also make Gemini just easier to use for everybody. We've got the new dynamic scheduler, which is very fast, supports multiple facilities. We're adding the Tom Toolkit integrations for the archive and dragons and GPP via goats. So thank you very much, and I'm happy to take any questions.
All right, thank you, Brian. Questions? Yes.
Thank you for the nice presentation, Brian. This is Andy Howell. So I'm really excited about the new scheduler, but I'm worried that if you train things on old schedules, the old schedule was not built in the greatest way all the time, in my opinion, because there were all these rules like you had to be band 1 to be in the, you had to be in the top tier to be, to get TOOs and all these other things that this scheduler will make. We'll do better than that in principle. And then my other worry is that a greedy-ish algorithm is not truly optimal. It's like what astronomers do when they're building a schedule, but it's not. But you could do much better. So have you thought about simulating a bunch of different kinds of schedules, and then seeing, using different kinds of algorithms to see what would actually make the best schedule?
Yeah. So yeah, all good points. We figured we want the scheduler to be at least as good as the human. So which is why, that's why when we're comparing it to what the past plans were, that's sort of, but we're quite open to new things and doing things in a different way. We've actually tried to think of first principles and how that could be done better. We're certainly open to that, especially with the new capabilities in GPP. We will do things in a different way. We may be able to change some policies around TOOs because we'll be a little more flexible. There'll be less of a distinction between like the rapids and the standards. So we're going to start sort of where we're familiar, and then we're open to changing, improving things, including the algorithm. When we started the project, we did do a trade study of different algorithms, including ILPs, like what Las Cumbres uses, a few others. We went with this one because we had full control of it. It was fast. We have control over things as the schedule builds up, like putting tellurics in the right place and things like that. But I'm certainly open to trying new things in the future. We're building it modularly, so hopefully we could put in different optimizer algorithms in the future. And yes, it doesn't do a full mathematical optimization, but it's close, and it seems to give quite reasonable plans. So it seems like a good place to start.
All right, thank you. Any additional questions?
Hi, Brian. This is Jianxiu. Very nice talk. So I just want to follow up on the scheduler. So I know Suvo, they also try to do a little bit like that and then do with AI. I think this really makes this take a snapshot of the current situation, right? Current condition. But then the major issue there is that you cannot really predict the weather. So, you cannot see the weather. So can you use like some AI tools and predict the weather pattern and then loop that into your scheduler?
We would love to. That's a whole different project, but it's quite related. But something I would like to do is work on some sort of machine learning AI thing that would take all of the available conditions information from the wavefront sensors, from the data reduction pipeline, from forecasts, try to assemble it and determine what are the current conditions now and what could they be for the next few hours. So if we can find a few people to work on that, that would be awesome. But we need to get GPP just up and running first, and then we'll try to improve the weather predictions.
All right. Well, thank you again for the talk, Brian.
Yep, thank you.
All right. Our final presenter here of the session is Joshua Haislip. He'll tell us a little bit about Skynet.
Perfect. All right. Yeah, I was trying to set this up so I had both hands to drive. Most of this is going to be a demo. And it's also it's the first time we've tried demo it all in a live fashion. So hopefully it goes well. Yeah, my name's Josh Haislip. I'm a software engineer working on the Skynet Robotic Telescope Network. And I just wanted to kind of go over the stuff that we've put a lot of effort into for the past few years. There was a point where we decided it made sense to take everything we had learned over the past 20 years of doing this and try to just put it all into a complete rewrite of the system. That seemed like a great idea at the time, but then we all know how that goes. What we thought would take a couple of years ended up, I think we're now probably into the 4th or 5th year working on it, but I'm really happy with where we're at and what we've done. Like I said, most of this is going to be a demo. But I will just briefly mention a little about Skynet. So we are a federated telescope network, so it's kind of different than a lot of other networks. What we do is we don't own a lot of the telescopes that are on our network. We have people come to us and they say, hey, I've got these telescopes, I'd like to put them on. The issue is we can bring them on the network, but they still own their telescopes, right? So we have to provide them some amount of autonomy. And they still need to have a way to control their systems. But part of the reason for putting your telescope on Skynet is that we've worked really hard to provide ways for people to exchange access to their telescopes. So that's a challenge that we have definitely taken on, and I think we've done a decent job with it and a much better job in the next version of our system. But one of the biggest challenges is the fact that every telescope that's put on our network is very different than the other telescopes. I don't think we have a single telescope that is an exact copy of any other telescope, including we have a 20-meter radio telescope at Green Bank, and we have 16-inch optical robotic telescopes in Chile. So it's a very diverse collection of hardware that we have to work through. And I really like what I saw in Brian's demo of the new control software for Gemini, because I noticed that one of the things that we've learned over the years that's really important in a system like this is you have to try to decouple the data that's being requested, the data requests, from the actual way it's acquired, right? And so a lot of systems that are out there ask the astronomer, what's your exposure time going to be? What filter do you want to use? That only really applies to a single system. And in Skynet, every system is different. So if I go out and ask an observer to give me that information, they better tell me exactly which telescope it's going to go on. And in our system, there's a lot of times that we don't have that answer. The observer doesn't know what it's going to go on. So we've spent a lot of effort doing exactly what I just saw Brian demo, where he was asking the observer, tell me about your data that you need. Tell me, give me requirements on that data. And then he was presenting the options as to the ways that it could be obtained. All right, demo time. Shortest slide presentation ever, one slide. Hopefully this all goes well. 2 things to note. This is a full stack installation, a dev installation running on my laptop. My laptop is very old and it's trying its best. So if we run into problems, we're going to blame performance issues on this poor little laptop here. I'm hoping that sharing my screen via Zoom is not the straw that breaks the camel's back here. But because it's a dev installation, I actually run an initialization script that kind of sets things up in a way that's good for presentations. Do not worry if you see a telescope moving around during the day taking images. Don't worry if you see a dome open. This is all local. I have the API server running, the web server running, telescope control software running, pipeline, all that's done right here, right on my laptop. The other thing is, we are firm believers in the API first design. I know that there are a lot of fans of that approach here, but we absolutely have taken that approach. We've made it so that what you see here, our new website, is an SPA. It's a single page application. For all intents and purposes, it can be this isolated thing that is strictly using our API. So everything you see done here can just as easily be done directly through API calls. And our API has think the last count, well over 100 different endpoints for different resources. Some of those are WebSocket endpoints for being able to do some pub sub, so subscribing, publishing information, and others are RESTful endpoints for creating resources and modifying them. I'll scroll down because I feel like I have to have the obligatory AI-generated galaxy that makes absolutely no sense from a science perspective, but we're still working through things. So let me jump over to the network page. So the idea behind Skynet 2.0 is I want to make it so that anyone who owns a telescope can come to this page. They create an account, they create an organization, they add their telescope information, they add their observatory information, they specify what devices they have, put those devices together into the instruments that they want to make available, and then they install software, and I wake up the next morning and find that there's 10 new telescopes on. That's the vision, that's the dream. We're working towards that. One caveat, though, is that I don't want to wake up and find that there's 30 new simulator telescopes on. So we're going to probably make this page our featured telescopes. So we'll be doing a vetting process to, of course, go through the telescopes that are automatically added, make sure that they are who they say they are and they're creating good data, and then we can feature them on a page like this. We will definitely provide a lot of information in different formats for showing what's available on the network. On the featured telescopes list. Also, when I said at the beginning that I want to make this a platform for end-to-end astronomy for everyone, I need to kind of step back a bit and explain a little of what I mean. We do a lot of education and public outreach. We also do a lot of science. We need to make a system that works for everyone. So at the end of the day, if I can have professional astronomers using a system, and it's the same system that I have a high schooler using, or a college student, or the general public, that's what I'm going for. That's what we're working on, and that's a challenge in itself, but we definitely have identified ways that we think we can make that happen. So some of the things you'll see on the page might not necessarily have a direct fit in the context of science, but you can certainly see how the point of this would be to make it more engaging and interesting and interactive for maybe other audiences. One example of that would be Skynet Live. So I worked quite a bit. It was a little bit of a programming addiction where it was one of those projects I couldn't walk away from. I kept saying, I'm going to add just a couple more features and that's it. But this is using Pixie.js. So behind the scenes is WebGL. But it's really just a general purpose stereographic projection of position vectors. And then on top of that, I added some plugins and made it so that I can continue to add plugins to build in and expand the functionality of it. And so what once just started as let me show some stars, then became, well, let me just turn this into something that I can, you know, turn the ground on and off, right? So it feels like you're out in space. And it's fully interactive, so you can move around and see things. And I've got this little bar in the way here. Let me see if I can move it. Select different observatories. So in our live view, this will be a nice place to go to see, hopefully one day, hundreds of crosshairs zooming around the sky, right? It's also accurate. We built it we were careful in designing it. So you see the moon jumping. That's actually the parallax because we're moving from North Carolina down to Chile when you're clicking on the different telescopes. You can do all sorts of really neat stuff. I could probably spend the rest of my time talking about it, but I think that there are other things I should. I will say that we did pull out functionality because that's the example of me using SkyChart and kind of here's a live status view of our system. There are other cases where you might just want to provide that as kind of a standalone tool where you can do other neat things like turning off the atmosphere and maybe turning on satellites. And let's see if we just speed time up a little bit. We can see satellites doing zoomies around the Earth. We can turn on and off Earth's shadow. So lots of cool stuff. Great for visualization. And you're going to see it throughout the page, right? So there's going to be lots of places you'll go. Is that SkyChart? Yes, that is definitely SkyChart. In fact, you might have noticed on the home page, that background. Yes, that's SkyChart back there hiding. So yeah, just pointing out that it's one of the tools that we'll use, and I think it'll be really helpful throughout the whole stack. A little the About Us page is pretty straightforward. Support, we are building out support documentation. I don't think many people like to do documentation. I am not one of them. We're working on it though. I want to stop for a second and jump over to a couple of diagrams to show some things that I think will be helpful before I move into the really cool stuff, like adding observations and requesting data. So this is our observation model. And we've basically defined an observation as coming in 3 different kinds. You can have an instance of an observation, you can have a draft, or you can have a template. The template's really important. I'll mention it a little bit more later, but you can imagine scenarios where you might want to fully spec out an observation and then be able to reference that to quickly generate new observations. In that case, you really want to treat that first observation as a template that you're cloning into other observations. The draft versus the instance, we use a draft publishing design. So it allows astronomers and observers to submit your observation. It's live, tasks are being scheduled. Maybe you want to make some modifications to that. Through the API, you can generate a draft version, make those changes, and then when you're ready, publish those changes instead of taking the risk of making those changes directly to the live observation that's already being observed. We divide an observation into kind of 2 main parts. There's a lot more to an observation than what's being shown here, but we have data requests and a target. And so the data requests are where we're basically allowing you to tell us the type of data you need. Don't tell us how to take it, because the second you tell us how to acquire the data, you're now boxing us in on very specific instrument or instruments of the same type. So if you're going to add a optical imaging request, give us an idea of how bright your object is, give us an idea of what your target signal to noise ratio is, and let us work out, understanding the details of the instruments, let us work out how many exposures, what the exposure time should be. Right now, we have 3 different flavors of data requests, and those, obviously, there's going to be many more that we add. The observation can include a mixture of data requests. So I think that's really something that's unique about Skynet, being able to say, here's my target, here's my observation. I need this type of data, and this type of data. Let the system work out figuring out what telescopes you have access to and figure out how to actually make that a reality and obtain that data. And it's all in one place, all in one observation. I'm not going to spend a lot of time on targets here, but you can see that targets have a saturation brightness model, a target brightness model, and of course a position, which comes in all the expected flavors and forms. Infrastructure model. So on the other end, that's the observer's side. On the other end, we can look at it from the telescope owner's perspective. And we can say that we allow, when someone creates an observatory in the system, they can create devices, representations of their devices. And in the case of an observatory, at an observatory level, you might have like a weather sensor as a device that you would like to represent in our system. The telescope level gets a lot more interesting. Obviously, there are a lot more devices that you would consider to be a part of a telescope. And so this is where you're going to specify things like rotators, cameras, OTAs, focusers. That's all kind of optical side, but we have radio antennas on the network, so we have to be able to handle that. So we also have worked really hard on defining what devices exist in the scheme of a single dish antenna and are using those to then allow the last step is to take all those devices and to put them together. Allow the telescope owner to say, I've defined all my devices, I've told you what they look like, here's how they fit together into one or more instruments. And so we have optical imagers, we have radio spectrometers. I'm sure that that list will also grow. That then gives us all the information we need to take the observation requests and to take all of the instruments that are available and to pair those together and give you an idea of what that observation would look like on each of these instruments. So I mentioned that we've spent a lot of time trying to work through how to facilitate sharing time across observatories and across telescope owners. I just want to spend a second here going over what our telescope access model looks like. So we define a telescope as having a single owner, but the owner of the telescope can go out and say, I want to identify these external entities, and I want to grant them access to my telescope. And in doing so, it's not just global access. Obviously, you need a little more fine-grained control over it. So when you're granting access to external entities, you can actually set up queues, and it's fully customizable within your telescope. So you can have a general purpose observing queue, a TOO queue, or maybe a maintenance queue. You order those, you prioritize those queues. Within those, you can reference the entities that you want to grant access, and you can provide them, you can configure the prioritization of those on a per queue basis. So sometimes it might make sense in the general observing queue to go with a ownership model where each of the entities has a certain number of shares of ownership. And what we will do is we will adjust the prioritization when we're scheduling tasks on the telescope in order to make sure that each owner gets their fair share of the telescope time. TOOQ, maybe you use a schedule instead. Maybe you want to, we have it set up so that you can choose to prioritize based on a schedule. We'll automatically adjust who is the top priority at any given moment so that when observations appear in the TOOQ, we're going to sort them based on the entities and based on their current prioritization. Put it all together, and then we'll jump back to the cool stuff, is you can see in a model like this where you really encourage the sharing of telescope resources, you can easily end up in situations in the new platform where you have two organizations that each have one or more telescopes, and they've got time, and they both have, they've both set it up to have a general purpose and a TOOQ. They can easily come together, go to the new website, create a new organization that is their new follow-up consortium, right? And all they have to do is go back to each of their organizations and say, all right, let's give access to the new consortium. And so in this example, they've given access to both of the queues. The consortium then, the admins of the consortium can go out and bring members in. They can possibly advertise to get other organizations to provide access to their telescopes. And within the consortium, they can set up observing accounts is what we use, where an observing account is what's tying users and their observations. It's allowing those users and observations to go to certain queues. It's kind of wiring that up, right? So to complete the picture here, imagine having an alert integration turned on in Skynet 2.0, where an alert comes in, you've set up your subscription, you've created your observation template, right? That paints a picture of the type of data you need. That template will, alert will automatically take the template, will generate a new observation, will overwrite the information you need, target information coming in from the alert, and you've already configured it to go right into this TOO observing queue. So just like that, that observation is now available on both of the TOO queues of both of the telescopes. You might want to have a separate observing account for follow-up. Lower priority, but it's doable, right? You just create a new observing account. You can organize this however you want or however the consortium wants. But the idea here is to facilitate allowing each independent entity in our network to either come together to form a new entity that can work together or to exchange times directly, which you can totally do as well. All right. What does it look like when we put it all together? So let's jump back. The first page that you've seen here is kind of the landing page view. So this is what everyone will get to see regardless of whether you have an account. Let's jump into my personal space. This is because I created an account, every user or organization has their own space, kind of like GitHub does it. We can see that as a brand new user, I actually have this First Light account. So that's something neat that Skynet's going to do as an organization within the network. Skynet is actually going to make it so that we'll have a lot of time on many different telescopes, hopefully. So one of the cool things I want to do with it is I'm going to create this First Light account, and I'm going to have a curated list of telescopes, and I'll make it so anytime someone comes to Skynet and creates a new account, I'm going to give them access to that First Light account. So right away, as a brand new user, without having to beg or ask for telescope time, you'll be able to immediately see that you have access to some telescopes through the First Light account. Here are the telescopes and the queues that are available. And so I can go in to try to add an observation. And so this is the third view, the adding an observation view. Remember I said we need to make this work for everyone? It's not going to work if we present middle schoolers or high schoolers or even college students with an advanced interface for submitting an observation. So we've designed this so that there are many different interfaces that we will be able to build. The project-based interface, you can imagine looking like this, where you can present this to a student or the general public and say, what are you trying to do? We will create the observation for you. I know that the audience I'm speaking to now would probably rather me spend time on the advanced interface. So advanced interface is going to ask you which observing accounts you want to use for your observation. That's tying you to telescope queues. Once you've selected those, you can now choose what type of data request you want to add. In this case, we're just going to add a data request that is for optical imaging. I'm just going to select a filter. Don't have time to go into what a filter group is, other than to say that, once again, don't ask the user to tell you a specific filter, because if someone says they want the clear filter, I only have 2 telescopes that have that. Maybe they'd be fine with the open filter or the lume filter. So instead, we let the user give us a list of filters that they're good with, and then we can work from there, and we can make it so that there are a lot more telescopes that might be able to complete their request. For this demo, I'm going to use time-based, even though I told you we shouldn't do that. But it makes a lot more sense than using signal to noise when I'm going to be observing during the daytime on a simulator. We'll add that, and you can, of course, add as many as you want. Here's our beloved sky chart again. Let's just select a object here. And we do allow for a lot of extra configuration to go into at a global level to give you a little more control over those optical imaging requests. And so we can switch to Aladdin here. And this is very similar to what Bryan was showing, in the sense that you get to this step and you say, well, you know what? I'm not just looking at this thing. I'm looking at a region, right? So let me turn on this region that we want to look at and specify the size. And then we can, after specifying the size, it's going to load in the available instruments and overlay the field of view indicators to show you that tiling's required or tiling's not required. You can tweak your settings to get an idea of which instruments will work best. And we'll just submit that, because I'm probably not even going to have time to go into Skynode, which is our telescope automation software. You can see it's running in the background in simulator mode. You can see that that task was just generated. And so Skynode also is just using the API here. It's reaching out via the API. It's getting the tasks that have been scheduled for it. It's moving the dome. There's our sky chart again. Moving the dome. This is a plugin showing where the dome is currently aligned and where the optical axis intersects the surface of the dome, so you can get good alignment. This software is already connected to all the devices. It's actually streaming device state back to Skynet through those WebSocket endpoints, which means that telescope owners will be able to come straight to the page and get additional information no matter where they are on current telemetry from each of the telescopes. You can see that information here. And of course, we've also built in the webcam support, so you can have a place that you can view the webcams related to your observatory. One final thing, since I'm running short on time, is what if we come back in here and we select the same observing account, but I just wanted to show an example of radio tracking, because I think this is really neat. Once again, don't ask the user to pick the actual back-end configuration and modes. Just ask the user what are the frequency windows they're interested in. So we can choose frequency windows, set constraints on what those windows look like, and what the minimum spectral resolution you need. We do need to switch here really quickly to the UTAS site, and if we just blink our satellites and find a good one, that one looks pretty good. And so just like that, we can submit an observation to track a satellite. But this is currently set up to be prompt 5. So let me just stop this, because the beauty of simulators and using the exact same software allows me to come down here and say, I'm not really prompt 5 now. I'm going to be this UTAS 14 meter. This is going to use the same driver we use on the GB20, so it's streaming position vectors to an operational control unit to make sure that we stay on target. You can see that we started slewing, and we are heading towards that satellite. We should be heading towards the satellite. This is one of the challenges of demos. Let's see if we go of live demos. Let's see if we go here, and we go to telescopes. We take a look at this. Let's see. Does not look like it's doing it. Well, this worked perfectly earlier. But we definitely can track satellites, and it works very, very well in terms of being able to pick up satellites as the Earth rotates. We can submit a single observation. We can have the satellites in. Our API provides the full ephemeris, so each of the telescope sites are pulling in that ephemeris. We stream those coordinates to each of the antennas, and one antenna will pick up the satellite as the other one loses it. So it's, yeah, so there's a lot here. I think I'm out of time, sorry. But I certainly am open to questions, and I'll be around and would love to answer any. So the plan is next summer, hopefully this all deploys, and then finally we get to, I know that AEON Live's been waiting on us forever because we keep saying we're so close. But yes, next summer after we deploy and we've worked out all the kinks, we have an SDK, Python SDK. So I've already spoken with some people. It's going to be super straightforward for AEON Live to just be able to wrap right around that and make it so you can submit the observation requests. Okay.
All right. Questions for Joshua?
Really cool stuff. Thank you so much. Do you want to mention a little bit about first, how many radio telescopes are there and what are the main challenges or differences to incorporate radio telescopes as compared to the optical ones?
Yes. So we were funded a few years ago to bring additional radio telescopes online. And so in the next 6 months, we'll be adding 2 more in Tasmania. One, I think that's mainland. Is that where Seduna is? I think it's called Seduna. It's Australia. So the radio side in the implementation's not been something I followed too closely. But then we'll have a couple more being added in Perry. In North Carolina. And the hope is that when this becomes available, obviously we are a if you build it, they will come sort of thing. So the point is once we get this out there and have available control systems, and we've worked out how to buy off-the-shelf components at some of these and some of these radio telescopes and put them in a way that then our software will work. The drivers that we're writing to communicate with them would work. So we'll also hopefully be a resource for other radio telescopes that might want to join. We can say, well, this is a pretty easy solution, relatively easy solution, right? Buy these things and it will just work.
Hi, it's Mark at Las Cumbres Observatory. Under the hood at the telescope control end, are you ASCOM, IndyLib, or is this entirely new?
So this is actually all Python driven with the exception of the front end. I'm using Tauri as the OS bindings, but that's just allowing me to use a lot of the same components. So I'm using Angular for the GUI. But as Python right now, I've just got the ASCOM drivers written. But we're defining our own driver interface, and we're doing it in a much more abstract way that basically says you, as a mount driver, you just have to implement a start tracking and you have to tell me whether you are on target, right? And so I hand an astrocord instance that's either scalar or non-scalar, time series, right, the ephemeris, and that's what that driver, when you implement it, must accept. And as long as you can write a driver that accepts that, which is what we do for the radio antennas, right, you hand that sky cord that's showing where the satellite is, and the mount driver, if it can support it, is supposed to get that antenna in position and follow that. Does that answer the question? Okay.
Just clarifying. So you said that the platform that you just shared with us today is not deployed.
Correct. So we're hoping that will deploy in next summer.
All right.
So we've started transitioning some of our telescopes over and testing on it, but.
Okay. And then the follow-up question being, obviously you have this network of telescopes that already exists and is executing. So what's your workflow without a platform like this right now?
We already have, so we have Skynet 1.0. We have our current version, it's a web interface, but it's 10 plus years old. And so it does what we need it to do right now. We have thousands of students and a lot of astronomers that come to the page and submit their request, but it's nothing like this, right? So it's very limited because we've kind of locked it and frozen it in development while we're working on this. So we are functioning as a network. We do obtain lots of data. We operate the radio telescope at Green Bank, the 20 meter, but this is going to make it so that I feel like we can expand a lot more.
Okay, thank you.
Yeah.
Yeah, so I just have some questions about the user base. So if I'm a high school student, I can join this consortium with nothing. I can just say, hey, here's my email address and I want these observations. I can join. I don't have to pay a
That's the
membership
idea.
fee.
Yeah, I mean, that's what my
Okay.
vision has been, is to
Huh.
make it so that as Skynet, part of the cost of joining right now is that a telescope has to give us time. And so they take advantage of what we've done and the network and the resources, and we get some small portion of that telescope's time. And then what we do with it is science and education. And in that case, yes, a student would just come to the page and create their account. Like, they don't have to join a group or anything. It's just like
And
creating an account.
same with the professional astronomer, or no?
It would be the same with a professional astronomer, but remember that this will be the first light account, and the first light account is just time that we are putting together from telescopes, likely small telescopes, to just, make it so that people who create an account can have a good experience and do a lot of neat stuff.
Okay, and so I have a small telescope and I want to contribute it, or I have a telescope, I have a huge telescope, whatever kind of telescope. I want to contribute it, I want to join this Skynet. And my fee for joining Skynet is I have to operate my telescope, I have to do all of the maintenance and stuff like that, but you are going to take some time from you're going to allocate some of my time, and that's the fee for joining. There's no other fee.
Correct. Right now, the model is that telescope that you've put on, you would be required to add us in your TOOQ.
So,
right?
I mean, simple question, who pays the bills? What's your funding model?
If you're a backyard astronomer and you've got a telescope, then you already have your telescope there.
But like, who pays for your servers?
Who pays for us?
Yeah. Who
Grant
make
funded. We are grant based right now.
So
and we are able to sell some of the time that we do get. So we receive time on telescopes from people, and then we are able to have people come to us and say, I want to buy more time. Do you have any? And we say, yes, we actually have received time from entities. And we're able to sell that.
But if I'm an astronomer, I get my account for free on the first. There's other telescopes that are not in the first light account, and you're selling their time. So you're a broker of telescope time. I'm just trying to understand how it's working.
Yeah. So in the current form, the way Skynet 1.0 works is that we don't even have the ability to create a new account. So we're entering new territory here, right?
Right.
And so we're still working through it. But my goal was to make it that the first light account's not, I don't think an astronomer is going to be using the first light account. We might have our own proposal system. We are still working through the details, right, of how that would work. The first light account will just be a way to hand a few credits to the high schooler or the kid that's really interested, or the general public, take some images of Jupiter and be able to, do stuff with those images.
But to pay the bills, you're doing grants plus telescope time sales, just so I'm clear on that.
For some of our telescopes that we own in Chile, yes.
Got it. Okay, thank you.
Mm-hmm.
I think we have one more question over here.
What is your quality assurance and user support model? You have now 10,000 students signs up. They all want to observe Jupiter. They want to know, how do I do it? Whom do they contact? Or the astronomer is saying, oh, all these images are elongated I got. Who are you going to blame for the bad image quality?
Yeah, that's a great question. So the plan is, in part of the plan for the Skynet SDK is that we will have tools that are going to do quality assurance, and they can run at the telescope. And so hopefully we can catch those problems before the image is even uploaded. After the image has been uploaded, we will, of course, do the best we can to look at that image and analyze it through our pipeline and say, yeah, this is not what the person requested. So hopefully we can catch it there. For education, we have spent a lot of time over the past decade building up tools that are external right now, but full programs that college students currently use in their astro introductory lab that's filled with that sort of information as to what do I do and how do I use it and how would I analyze this data. And then in terms of scalability, another thing that we do, and we do this in our current version of Skynet, it's not exactly scalable. If you think about having 1,000, 5,000 students that show up and say, I want an image of Jupiter. But one unique thing that we do is, you saw that I had that project-based interface, right? One of the reasons for doing that is, of course, to make it easy to use. But the other reason for doing that is I can kind of funnel people through to specific requests. So I might end up with 5,000 people that all want an image of Jupiter. What we can do in the task scheduler is we can look at that and say, everyone at all 5,000 of the people want exactly the same image. And so we can go, and instead of taking 5,000 images and spending the rest of the night taking images of Jupiter, we can go take that image once and everyone gets that same image, but it was taken for them, right? That is your image. I know, that's the trick though. We will never provide catalog data. That's one rule that I've made, that we will never just pull a catalog image and say, here it is, someone took this last night. But if there's 5,000 people out there that all want one image of Jupiter with the same exposure time or the same signal to noise or the same filter, I'm not going to sit there for the entire night and 3 more nights taking images of Jupiter. So we will take one image of Jupiter, and that's our way to scale so that we can actually support a much larger audience and user base.
All right, I think that we're about out of time. So thank you again, Joshua.
Yeah.
All right, and thank you again. That was a fantastic session. Thanks to all our speakers. And I think we're break time. So back to you, Rachel.
And thank you very much, Cam, for moderating this session. Appreciate it.